All right, chemistry students, we're going to continue in chapter 9, and we're focusing on concentration, and then there's going to be later sections where we'll look at things like electrolytes, okay? But concentrations of solutions are the main focus of this particular video, okay? So what exactly is concentration? So remember, solution is composed of solute and solvent. Okay, those two parts come together into a solution. And so really this is just the amount of solute relative to solvent. That's all concentration means. Usually it's an amount of solute, kind of you're thinking in a fraction, on top over or divided by an amount of solution, the whole solution, okay? The main one that we are going to see, or the main one if you took maybe chemistry in high school, is molarity. And that's the one that's really common in a lot of chemistry labs and undergraduate science labs. But in medicine and in nursing, like on IV bags, there are a lot of other ones like these percent components, and you really do need to know all of them. You should recognize all of them. But in terms of calculations and conversions, we will see a lot with molarity in this video, okay? So let's define molarity. Molarity is simply moles of solute divided by liters, volume, liters of solution. So if you had dumped in solute, that's what this is trying to show, the amount of solute, and then you have a certain volume of solvent that you're adding to make up the whole volume of the solution, okay? Molarity is abbreviated capital M, and I'm focusing on that because there's a lot of M's in chemistry, and I really want you to write, if you were writing, say, a solution that had a molarity of 2.0, make your M super clear that you know that that's molarity, okay? And you need to know that that big capital M actually stands for moles of solute over liters of solution, not, for example, over liters of solvent. It's liters of solution, okay? So how would we actually read that like 2.0 big capital M, okay? So here's just an example with a 1 capital M NaCl. So we don't actually read it 1 molarity sodium chloride. We kind of abbreviate the word molarity, and we use this new word molar. Okay, kind of like the molars in the back of your teeth, back of your mouth, your teeth, okay? So just like that word. So we would just read it as like a 1 molar solution, and that means there's 1 mole of sodium chloride for 1 liter of solution. But we don't write the 2 units, moles over liters, like that. We often just write it out as 1 and then big capital M and then whatever we're working with, in this case sodium chloride, okay? So I would read that I have a 1 molar sodium chloride solution, okay? And you, like I said, you definitely need to know that that means moles over liters, okay? So that's the first one. You have a table in your book, this table here, that lists molarity at the bottom, and it's got solute and then overall solution components, okay? But it lists several other ones. I already mentioned the mass percents, and I listed out the molarity down here at the bottom with an abbreviation. So let's look at the percents for just a minute. We are going to go through some calculations with molarity, and later in the chapter we'll see this other one, molality, which is why I've added it here. Okay? So the percent ones may sound confusing initially, but really all it is when you're in the lab, you might actually be weighing out a mass of substance, that's a solute, and your solution, while it could be a liquid, you can have the mass of that liquid as well. So you would just measure out the appropriate, say you had 10 grams of sodium chloride, 10 grams of water, and you would have a percent, and you would label it on the sticker on the bottle, M over M percent, mass over mass percent. And so if you see, you could break it down so that it is a volume over a volume as well, okay, as long as they're the same units. You couldn't have like milliliter over liter, okay? Do you see that? No, any units as long as they're the same. So they could be liter over liter for volume over volume, okay? And then you could have a very, very common one in medicine is mass per volume. Mass per volume. So M over V, mass per volume percent. Okay? That's a common one on IV bags and stuff in medicine. And as you go through examples and stuff in the homework, maybe you'll be more familiar with these. Like I said, they can initially frighten students because you see this percent and you're like, oh my gosh, this unit has got a huge label. But it's actually just, if you're thinking like you're in the lab, oh, if I'm weighing out, it's actually kind of easier than molarity. If I'm weighing out 10 grams of sodium chloride and I'm dumping in, and I have a total solution of 100 milliliters of water, that's it, 10 over 100. And then whatever that computes to be is the label you would put M over V. Just so you know, sometimes the mass isn't an M, it's weight, W-E-I-G-H-T, weight. And so you may see, like if you were to look online, you may see W over W for weight over weight. It's the same thing as mass over mass, okay? Okay, so while I'm on concentration units, I want to define this molality. Since you see they're all solute over solution, molality is a little different because you have moles of solute, just like molarity, but the denominator is actually kilograms of solvent. Okay, so we're going to see that later in a later video, but I wanted to show it to you because the abbreviation is usually kind of a lowercase italics m, which is different from molarity, and that's why I say make your molarity like big, like McDonald's golden arches. Make your molarity a large M, okay? So that's really, really important. One other comment. If the density of water is 1 gram per milliliter, then, so 1 gram per 1 milliliter, then if I have 100 grams of water, I know that it weighs that volume is 100 milliliters. If I have 100 milliliters of water, I know that that weighs 100 grams. If I have 200 milliliters of water, based on the density, that is 200 grams of water. And so if you were given a problem where you had 200 grams of water, you could potentially use a mass volume or a mass type of label on that concentration component, okay? So we're going to zoom in on the next slide on parts per million and parts per billion, okay? So this is a million, 10 to the 6th is a million, and 10 to the 9th is a billion. So what does that actually mean? Basically, if you have a really, really small amount of solute present in a larger volume, then it's more convenient to use this unit ppm or ppb, okay? So parts per million, you're thinking mass of solute over mass of solution times 10 to the 6th. Or you could do it in terms of volume times 10 to the 6th. Okay, the table on the previous slide showed the 10 to the 6th part, but it didn't give these two sort of options here. Okay, and billion is the same exact concept, except you're using 10 to the 9th because that's a billion versus a million. This would be actually important in maybe an environmental sense. If you have, I know there was a city in Michigan that had too much lead. So lead is not good for you to consume, to eat or drink, and they had a certain amount of lead in their water. And the news actually reported it. I can't remember if it was in parts per million or parts per billion. Another example would be if you're eating fish. Fish can tend to have some mercury. And you don't want to have very much mercury in your body because it's kind of toxic to your body. But you can eat a certain part per billion over your lifetime or whatever, and it'll generally be okay, but it has to be small. And like the fishing industry would have to report if they've got too high mercury in their fish, you can't eat it. It's illegal to eat. So let's look at an example with parts per billion while we're on it, okay? And then we'll go into some examples with molarity. So while part per billion, ppb, is fresh on your mind, keep these formulas fresh on your mind here. Let's look at an example. So it is known that the maximum amount of chloroform, which is this formula here, in drinking water is published probably by the Environmental Health Agency or something like that to be 100 parts per billion. If you have drinking water with more than that in it, chloroform's not good. And if you're like, what's chloroform? A couple hundred years ago, this is what they used to knock people out for surgery, like in anesthesia. But this is also the same bottles that they used to knock out King Kong. If you ever saw that movie with King Kong, it messes with your brain cells though, so it can give you headaches, migraines, and cause long-term damage. So all in all, we don't want to have very much of it in our body. So if I have a glass with 400 grams of water, and if you note, I made the note here, that's also 400 milliliters of water, and that you can simply do the conversion by using density as a conversion factor, okay? But ultimately, if you know 400 grams of water, that's 400 milliliters of water, and vice versa. They're the same, okay? So they want to know what is the maximum amount in grams of chloroform that can be allowed, knowing the part per billion is 100. So the same formula from the previous slide, except sort of the answer here. The number 100 parts per billion is on the left, and then I have the mass of solute over mass of solution times 10 to the 9th, that formula for parts per billion. So if you actually rearrange this formula, so you can either plug in the numbers and solve it, or you can rearrange it so that mass of solute is by itself, and that's what I did here. Mass of solute by itself, and then this is the rearrangement, and then you multiply by 100 parts per billion. So that's just the algebra rearrangement. From this part to this part was just algebra, and then this is just plugging in the numbers. The 400 divided by 10 to the 9th times 100. So you should get 4 times 10 to the negative 5 grams, or 0.04 milligrams. So that is a really small amount, 0.04 milligrams. That's like a speck of dust. That's a very, very small amount. So if you think about it, 400 milliliters of water, that's like half a bottle of water. You can barely have a speck of dust in there, and that's the allowable healthy amount of chloroform. So that's a reasonable response, okay? Let's look at a conversion with molarity. And like I said, you need to know these solution concentrations. So I re-put the molarity up here, the molarity moles over liters, okay? And that would make a great question on an exam. What are the appropriate breakdown units for molarity? And then a bunch of wrong choices and 1 moles of solute over liters of solution. Correct choice, okay? So if you in the lab weigh out, this is my example, 25.5 grams of potassium bromide, I went ahead and gave you the molar mass, and your total solution is 1.75 liters, what's the molarity? So the question mark here is molarity of the solution KBr. What's the concentration, okay? Well, before I can actually use the formula at the top of the slide, I have to use the molar mass and the given mass to determine the moles. I need to know how many moles are present in this mass. So that's just a simple grams to moles conversion that we've already seen in here, okay? So let me erase this because I haven't animated in. All right, so this is just a simple grams of KBr cancel, giving me the moles. This would be a perfectly good exam question. Where you're given something like this, you must determine moles before you can determine molarity. So now I've used this number, I've used this number. In order to determine molarity, I've got moles of solute given liters of solution. It's just a simple division to give me 0.122 molar potassium bromide. Okay? Let's do another example of that, okay? Same thing. And honestly, before you continue with the video, hit pause and see if you can solve this. So it's potassium nitrate, same thing. You're given a volume, you're given a mass, and then you're given the molar mass. Determine the moles first and then calculate the molarity. Should be a normal looking number, okay? So if you hit pause and then you solved it, did you get 1.53 molar? And I don't have my KNO3 here. There, I'll add it in. So potassium nitrate. So that's another example of using the molarity. Okay? Another comment about molarity is it can be used as a conversion factor. That shouldn't be a surprise. All these values that you've been working with throughout the semester can be used as conversion factors. So if I have a solution of HCl and I tell you it's 3.5 big M molar HCl, so you know there are 3.5 moles of HCl in 1 liter of solution. So your conversion factor might look like this, where you write it out as that equivalence. Or you could think of it in terms of, all right, I know it's moles over liters of solution, since that's what the big M breaks down into. And that would work if you were given a volume. If I said I had 6 liters of this, and I wanted to know, so 6 liters, and I wanted to know how many moles are present in this, I could just do a quick conversion, 3.5 moles of HCl, 1 liter, liters would cancel, multiply the two numbers together, and that would tell me how many moles are present in this 6 liters, okay? If you were given moles and you wanted to convert to volume, you could do the same thing, okay? Because you have the molarity here. This molarity, written upside down, is the image on the right, the conversion factor on the right. So that would be if you were given moles and you wanted to know the volume. In that case, this conversion factor on the right, moles would cancel out, leaving you with liters, okay? So we're going to talk about dilutions, all right? We're going to talk about dilutions. That's the next section. So dilutions, you're like, what on earth is that? So picture yourself in the lab. Here's a little lab bench, trying to draw somebody at the lab bench here. So a person standing at the lab bench, they got their goggles on, okay? They got their goggles on. There may be a shelf up here. So we'll make this thick. So this is a shelf. And this is the actual lab bench, okay? So they have a bottle up here, you know, that might be, say, 6 molar HCl. So we're talking high concentration, a high concentration. And for the experiment that day, they're working in their little beaker down here or whatever, and they need maybe a 2 molar HCl. And they're only working with maybe 1 liter that day, okay? So what they're going to do is, this is the stock solution. Stock solution. So in lab, you might have a bunch of high concentration stocks, okay? And then for the experiment that specific day, you would dilute the stock down to, in this example, 2 molar, okay? And there's a formula for that, all right? And you may see, I'll see it on the next slide, but it's MV equals MV. We'll go over what that means, but you sometimes see it as CV equals CV. Hopefully you recognize the V as volume. M can be for molarity, or you could just say C for concentration. Because you could do this with any of the concentrations we already discussed. You could do it if you had a mass percent concentration or any other concentration, okay? But I did not use any formula more in grad school than this formula here, okay? You use this in the lab all the time, all right? So in lab, on the shelf, way high, would be a stock solution. That's a high concentration solution, and you would make a lower solution. So lower concentrated solution for the experiment that day. Here's the equation for dilutions. The ones that simply mean an initial solution, that would be like the higher concentration, and 2 simply mean the final, okay? Here's an example of dilution that you've probably seen in your life and you didn't think it was a dilution. But we've got the concentrated orange juice that you can buy at the store, and then you dump the concentrate and it looks kind of like syrup at the bottom, and then you add a certain amount of water. In this case they say 3 cans of water, and then stir it up and you've got your more drinkable orange juice. So the stock solution in this case would be the whatever the concentration is of the sugary syrup. It would be that initial can, and then this would be the final volume. And so you could solve for the dilution. So that's an example. Medicine gets diluted a lot. Diabetics might have to dilute their insulin with some saline. Okay? So you need to know this formula. Let's do an example. I actually made up the 6 molar. I didn't think I had a 6 molar coming up, but here's the dilution example. So given a 6 molar stock of HCl, that's what's on the shelf. I need 3 liters that is 0.5 molar HCl, okay? So I have color coordinated my M1V1 equals M2V2, or like I said, if maybe you had it in high school and you memorized it, C1V1 equals C2V2, that is fine. I've color coordinated it. Make sure you match this 3 volume matches with this 0.5 molar, okay? It doesn't actually matter whether they're 1 or 2 as long as you pair them correctly together, okay? But I color coordinated. So the black V1 is what I'm trying to solve for. So you can plug in the numbers and solve the algebra fine, or for those of you that want to, you could rearrange it, leaving V1 all by himself, since that's what you're solving for. We need to know what volume to dump out of our stock solution, okay? And that's just what I've shown. This here is the calculation that I'll show here at the bottom of the slide, all right? So in your calculator, you're just multiplying the 0.5 times 3, and then you divide by 6. And so you would know you need 0.25 liters of HCl. Okay, so if you're doing this kind of thing on the homework, make sure if they give you the unit that they have it in liters, because they might trick you up and have like a blank and then ml, so you would need to convert that to be 250 milliliters, that kind of thing. So check your units. If you were given, on that note, if you were given milliliters, like here, you would need to convert it to liters, because if you're going to cancel out with molarity, remember molarity is moles over liters, okay? So if you're going to use this formula, you should really have all of your units in liters, your volume units in liters, okay? So I know that's a lot, but we are going to continue on to the next section. So that's all concentration, but I want to explain a little bit more about solutions and then go over one more concentration unit, okay? But we got to define a few terms here. So these should be fast slides in terms of definitions and stuff. We're going to define electrolytes, okay? And anyone that's drunk a Gatorade or a Powerade or anything like that, you've drunk an electrolyte solution, okay? So on the left is an electrolyte solution with ionic substances that are totally separated in solution. They're separated. Whereas like a covalent substance, like sugar, that would be what's a non-electrolyte solution. Okay, so those are the two definitions. Electrolytes completely dissolve in water. Remember, dissolve we talked about when we were defining solutions. The electrolytes are separating. And then the non-electrolyte, I'm not chopping this sugar, for example, in half. These things that look like little gobstoppers here, those are all the sugar molecules, and then all these little guys there are the water, the surrounding water. So we do not break up the sugar in the sense like the sodium chloride is separated into the ions and interacting through intermolecular forces with the water. Whereas the sugar stays together on the right, and therefore it's a non-electrolyte. So there's some properties of electrolytes and non-electrolytes, but before we get into them, we actually need to take this electrolyte and break it down further, okay? It's not that difficult. We're just going to break it into two types, strong and weak. Strong and weak, okay? That's it. So we'll have strong electrolyte, weak electrolyte, and then non-electrolyte. You need to know the difference among them, okay? Strong electrolyte, if you were to actually see it in a balanced chemical reaction, would have an arrow, a complete arrow. In other words, 100% we are on the product side of this reaction, okay? We have formed product. We're not really in this reactant side at all anymore. That's a strong electrolyte, okay? And there's nothing that you know in your knowledge of chemistry to know whether something is a strong electrolyte or not simply by seeing this on the left. What you need to recognize is the fact that there is a reaction arrow pointing to the right, meaning this forms the products and the reactant is pretty much gone. One of the properties of strong electrolytes is that they conduct electricity. So here we've got a solution of strong electrolyte, and they're trying to show two poles, the positive and negative pole. And then if you see, the light bulb is on. Okay, and it's bright. It's on, but it's bright. The weak electrolyte, you're looking for that equilibrium arrow, okay? And so this is actually kind of showing just double arrows here. In other words, this substance has some H plus, some F minus, as well as some of the original, some of the original HF reactant, okay? So we have some dissolving, but not all the way. It's a partial. And if you see, the light bulb is dim. It's on, but it's dim, okay? So it still conducts electricity, but it's a weak conductor. So weak electrolytes are weak conductors. There's nothing in your knowledge of chemistry to know that this is weak. You just have to recognize that the arrow is an equilibrium arrow, or you would have to say, oh, okay, that's weak due to the equilibrium arrow, or you'd have to be told, okay? You'd have to be told this is weak, and therefore is it going to be a bright light bulb or a dim light bulb? That would kind of be the question you would be asked, okay? So I want to make another point. Let me show you actually the sugar. This is a non-electrolyte. I'll get to the top of the slide in a minute. This is a non-electrolyte. So the sugar does dissolve. You see the aqueous? We do dissolve and we do have an arrow, but you need to recognize that this is not an ionic substance. So if you're not an ionic substance, you're going to be a non-electrolyte and the light bulb is off. We do have molecules dissolve, but we're not conducting electricity, okay? Another point about this dissociation in the electrolytes is if you have an ionic substance, make sure we've separated and balanced the reaction completely. So if you had to write out a dissociation, if you were told Na2S is a strong electrolyte, what are the products? You could make it clear, okay, you've written them out as the appropriate ions, and then you balance the coefficient 2 there in front of the sodium. Keep in mind, this bottom example here, the polyatomic ion does not dissociate, like we don't separate the sulfur and the oxygen. You need to recognize the polyatomic ions here. Yes, we've separated into 2 ions, but keep your polyatomic ion together, which we've already seen that in our balancing chemical reactions, okay? So I have 2 tables. These did not come from your book, but they actually show strong, weak, and non-electrolyte, as well as some components of how these work in solutions, and then some examples, so some stuff you've seen. So these examples, if you look, a lot of the strong electrolytes are just ionic substances, and I know we haven't defined acids yet, but you see there's actually a list of a bunch of acids. We're going to get to that in Chapter 10. This table shows a bunch of electrolytes in actually IV options. So maybe you've actually had an IV where you've had Ringer solution. It's replacing these specific electrolytes in the body that maybe was through dehydration. And in that Ringer solution, vets will actually use that in dogs that come in that are dehydrated and stuff like that. Okay? So that's a unique table at the bottom. You don't need to know anything in that table for an exam or anything, but it's actually a really good table, and you may hear these terms. You may hear 5% dextrose. Well, that's a probably 5% mass per volume sugar solution. So that's kind of interesting. Okay. All right, the last concentration unit is something that you would really only see in nursing chemistry, like a nursing, pre-nursing class. And what it says is, someone said, I'm in medicine and I don't really care about molarity, so I'm just going to use a new term called equivalence, okay? Equivalence. And equivalents are really only something you would see like on an IV bag in blood work. It's not going to be used in a lot of chemistry material, but basically for ions, the amount is going to be equal to 1 mole of charge. Okay, and so the abbreviation is EQ. It's EQ. And so like if I had 1 milliequivalent, there's the conversion, or vice versa. Okay, but I want to give you the actual, how do I determine the equivalence if I've got an ion? Hopefully you all know you've got potassium in your blood, that kind of thing. 1 equivalent of some ion that would be measured in blood work, would be the molar mass of that ion from the periodic table, so whatever that substance is, divided by whatever charge it makes when it forms an ion. Okay, so this formula that's in blue on the bottom, you need to know, and it's on the next slide with a couple examples here. Okay, so if I have a +1 or a -1 ion, the EQ, once again, is this blue formula, the molar mass divided by the charge. Well, sodium is 23 grams per mole in terms of its molar mass, so you would just say 23 divided by, sodium forms +1 divided by 1, and therefore the molar equivalent is 23. For a chloride anion, it is 35.5, okay? if we have something like magnesium or calcium that's 2+, or if you have something that's -2, you divide by 2 here. So 24.3 grams is what you'd see on the periodic table next to magnesium, but you would have to divide by 2. So the equivalent for magnesium would actually be 12.2, okay? 12.2 equals 1 EQ. You could even put a little G there. 1 EQ for magnesium, okay? So that is now a conversion factor you can use. These in this table down here are the common ions that are measured in blood work. And then if you see, they've got milliequivalents per liter of blood. That's the concentration, okay? That's the concentration. So we're going to do an example with calcium, and that's where we're going to end. But we're going to do an example with calcium, and I'm going to give you what a normal concentration is and an amount of blood, and then we're going to solve for how many milligrams are present. Milligrams of calcium. Okay, like I said, this particular unit is something that is really only in nursing chemistry. It's not going to be something you're going to find very easily in other general chemistry books, okay? Once you see the conversion, hopefully it'll be a little bit easier and you'll be like, oh, okay, I got it. So normal level is 5 MEQ per liter, and the question is how many milligrams are in 1 liter of blood. Okay, so this 5 MEQ per liter can be used as a conversion factor, okay, but we need to know what the equivalents are, okay, for calcium, because we're going to go from liter to milliequivalents. Okay, we can do that with what's given in the problem. That's a simple, it's almost kind of like the molarity conversion. The next step is going to be one where you're going to get thrown for a loop a little bit. But let's look at calcium on the periodic table, and you'll see that the molar mass is 40.08 grams per mole. Okay? So if we're going to determine the grams per equivalent for calcium, that's going to be 40.08, and you just write the gram divided by calcium forms +2, and you can just say divided by 2, okay? So you could write it out as 20 if you want, basically the 20. But one of the things that is unique about MEQ, okay, is, so that could be 20, we'll just abbreviate it to 20 EQ. This number, I can actually, I know this is going to throw you for a loop, I can make a conversion where I treat the numerator, I automatically put a milli in front of it, and the denominator, I automatically put a milli in front of it. Okay? I know that sort of throws you for a loop a little bit. Okay? The second conversion uses this number here. It uses this number here. Okay? I know that throws you for a loop, but if you follow this pattern, you'll be fine, okay? If I were just asked to find the equivalence of calcium, this math here, using the blue formula from earlier, is what you would use, okay? But you can do this, I know it's sort of funky algebra, you can do this with equivalence, okay? So here's the example, sorry. Do you see the molar mass divided by the charge? That's all I'm doing right here, except I'm adding a little m in front of it. And because I'm treating, I don't even need to change the numbers because I'm treating both the numerator and the denominator the same. Okay? So there's the value. And like I said, you can just stick the m in front of it. Just like that. You can stick the m in front of it and you don't have to change any of the numbers, which will help us go directly from millieq to milligrams. Okay? So on the next slide, I actually go through the work, all right? So here's the work. There's 1 liter of blood cancels with the 1 liter of blood on the bottom. This middle conversion factor was given in the problem, okay? This is the equivalence that we just, based on convenience of doing this with equivalence, we just stuck milli in front of both of them. If that bothers you, you can go ahead and do the conversion to milligrams, but that's if you get to illegally kind of put M in front of here, or legally do it, then go ahead and do that, okay? And you see milliequivalents of calcium cancel here with milliequivalents of calcium, leaving you at the unit of milligrams, okay? So then it's just the simple math in the conversion as you've seen with your calculator, and the answer is 100 milligrams, okay? So the next video is going to be properties of solutions. Thank you for listening to this. I know it was a lot of material, but get familiar with your concentration components. Thank you.